Hello everyone, welcome to the session Deadlocks, Understanding and Troubleshooting. Welcome to the PASS Summit. My name is Denis Reznik and we will start troubleshooting deadlocks very soon. First of all, I would like to ask you to explore PASS offers, including online and offline events, PASS Pro membership and PASS volunteering. Please evaluate this session after it will finish. Your feedback is very important for the organizers and for the speakers. My name is Denis Reznik. I'm from Kyiv, Ukraine, where I work as a data architect for company InTAP. I'm Microsoft Data Platform MVP since 2010 and an active member of SQL community. And here is our agenda for today. The main idea of this session is that we need to understand why deadlock was happened. When we will do this, when we will find the root cause, we will be able to find solution to avoid the deadlock. And in a lot of cases, there will be several solutions which we can choose from. In this session, we will check 11 different deadlock cases, their root causes, and the solutions to avoid the deadlocks. Besides deadlocks, we will check few more important concepts of how SQL Server organized concurrency, how SQL Server lock resources, and first of the concept is logs. We will check all the logs available in SQL Server except bulk update logs. And there will be no separate session for logs. All this information will be included implicitly into the story, as well as transaction isolation levels. Transaction isolation level define the rules how SQL Server apply locking and which concurrency effects we will have or we will have not in this transaction. By default, SQL Server use read-committed transaction isolation level, and if I will not mention that session use another isolation level, you can think that this information is related to read-committed. Okay? Let's start with the classic deadlock situation. We have two tables, cities and users, and we start transaction which update users. John Smith is moving from Kyiv to Houston. And to do this update, SQL Server put exclusive lock on the row number 4 in the table users. At the same time, second transaction is trying to change the name of the city from Dnipropetrovsk to Dnipro, and it put exclusive lock on the cities table on the third row. Now, first transaction is trying to update city table, and it can't because there is already exclusive lock on the row number 3, so first transaction will wait. Second transaction is trying to update users, and again this operation can't be finished, because this transaction needs to wait for transaction number 1 to release the lock. We have deadlock. No one of these sessions can be finished. And SQL Server has an internal process called deadlock monitor, which monitors these cycle dependencies. And if it will find something like this, he will kill one of the transactions. So one transaction will finish with error, second transaction will continue to execute. When SQL Server make this choice, he tried to kill the smallest transaction. Smallest means that these transactions will take less time to roll back. So, here we can say that we understand why deadlock happened, we understand the root cause. Deadlock is happening because two transactions update different tables in different order. And to fix this, to avoid the deadlock in this situation, we can change the order of these operations. We can update table users first in both transactions, and then update table cities second in the both transactions. Also, we can remove transaction if your business logic will be fine with this. And you see already we found two solutions, and we can choose one of them to avoid this deadlock. That was easy, isn't it? Now we're coming to more complex deadlock cases, and before that I would like to share some log concepts. First of all, shared logs. When SQL Server wants to read the data, in default isolation level read committed, SQL Server will put shared log on the row If the second process will want to read the same row, it will also put shared lock on the same row, and they both can read the data simultaneously. But if another process will come and will try to update the data and put exclusive lock on the same row, that process will wait in the queue before first two will finish. Next type of lock, exclusive lock. If process 1 is trying to modify the row, it blocks it exclusively. That means that any other process won't be able to access the data for write and for read purposes until first process will finish. And now we're coming to the demo which called common deadlock. For deadlock monitoring I will use extended event session. Let me create it here. I will call it pass deadlocks. As an event I will choose deadlock graph. That will be enough. In mostly all cases that will be, this single event will be enough to analyze deadlock and find the root cause. As data storage I will choose file. Okay, my session is ready. I'm starting the session. And now I'm going to the demo itself. There are two queries. This demo will be done on database Twitter, which contains tables, users and statuses. We will use default read committed isolation level for the both sessions, and here are the queries. First one will select ID, name and location from table users where name starts from Santa, and second query will do two updates for the same ID. I'm doing two updates here because if I will update Santa Claus to Santa Claus, SQL Server is clever enough to not do this operation at all. So I need two updates, but just one of them will be involved into the deadlock. Let me run these queries. After a while one of them will finish, and probably that will be select statement, because it's easier for SQL Server to kill this session. It is much smaller than update. You see clearly that this was a deadlock, and let's check what we have in our extended event session. Let me stop it. This is our deadlock. And we see here that bubbles here are the queries and squares here are the resources. So, as you see here, select query is holding shared lock on the non-clustered index by username and request shared lock on the clustered index. At the same time, update query is holding exclusive lock on the clustered index of the table users and request exclusive lock on the non-clustered index on table users. Here we have contention, here we have deadlock. Let's check why it's happening. To do this we need to go to the execution plans of the queries. Let's check the execution plans for the select. As you see, this query accesses both indexes, non-clustered index by username and clustered index PK users. Why it's doing this? Let's check. In the non-clustered index, it took ID and name, and from clustered index, it took location field. That's interesting. So, let's check how SQL Server put logs here. There is no visualization for logs, but if we understand how SQL Server works, we will understand how SQL Server will put logs and in which order. Each operator in SQL Server query plan have three methods: open, close, and get row. If operators doesn't have rows, it requests rows from the previous operator, and eventually nested loop will come to the index seek on username and request a row from here. Index seek will do data access, so to read this data, it will need to put shared lock on the row. Here we can be sure that this operator will put lock on the non-clustered index by username. And then for each row, due to nested loop join algorithm, it will request corresponding rows from this input. It will do lookup for clustered index and will put shared lock on the clustered index. And there is small piece of time between these operations. And in this time interval, another process like our update can put these locks in different order. And update actually will do this. Update will block first clustered index. At the same time, select query will put shared lock on the non-clustered index. Then update will try to put exclusive lock on the non-clustered index, and it will not be able to do this because it's already locked by the select statement. And select statement will try to lock clustered index and also will not be able to finish that operation because it already locked by the update statement. Here we have the deadlock, and SQL Server choose to kill one of the queries. In our case it was select. Okay, now we completely understand the root cause of this deadlock. What we can do with this? SQL Server is trying to get just location field from the clustered index. If we will remove location from this equation somehow, SQL Server will not have a deadlock because there is only one index on username and all the data will be just here. That's one of the solutions. This location field can be included in the index by username. That's another solution. We can use isolation level read uncommitted or hint NOLOCK for the user table to avoid shared locks at all. This will be another solution. And you see, again, after finding the root cause, we can find a lot of solutions to avoid the deadlocks. Now we're going to the next demo, which I called merge deadlock. Again, we have two concurrent transactions. First one, updates table users and updates table statuses in a single transaction. Second is the query which select data from statuses and users table. And this is a very important moment here. We're using non-default isolation level, which is called repeatable read. Let me show you the difference. Default isolation level read committed has this concurrency effect, which is called non-repeatable reads. Let's imagine we have table users with user ID and city inside, and we are selecting data from users where city equal Houston. SQL Server put shared logs on these rows while reading, and in read committed, SQL Server released these logs just after the row was read. Yes? So, when second transaction is coming and trying to update user set city key where ID equal 2, it can put exclusive log on this row and update the value. And when in the first transaction we will run the same select query where city equal Houston, this query will return 2 rows instead of 3. So in the same transaction, for the same query we receive different amount of rows. This is called non-repeatable read. And when we use repeatable read isolation level, SQL Server will hold shared logs till the end of the transaction. So we're selecting data from users where city equal Houston, and now update statement can't do this update because shared logs are still there. So second query in the transaction will return the same 3 rows. And only after this transaction will finish, update can put exclusive lock on the row and do the update. That's how repeatable read works, and this is the rule which this query will follow. Okay, let's start the demo. I'm updating the row, then I start my select statement, and I'm running my second update statement in the transaction. After a while, my transaction finished and my select statement killed because of deadlock. Okay. It's pretty clear here. We are updating table users and we put exclusive lock on the row in this table. Then we do the same for table statuses. Select query in this case do clustered index scan for table users and then non-clustered index scan for table statuses. First, second. Order is the same, but it's not the same because these two datasets merged by merge join operator. Let me show how merge join works. Merge join has a prerequisite. Both datasets should be sorted. So here we are joining table users and table statuses by user ID. SQL Server starts scanning first input, ID equal 1, then he starts scanning second input. If there is a match, this row go into the next operator in the pipeline. Match again, then new value, user ID equal 3. And at this point, SQL Server switch back to the first input and continue scanning it again until new value will come, user ID 4. Then he switch back to the second input and continue scanning it. So, as you see from this visualization, there is no predictable order of locking for both inputs. So, of course, if I know values, we can predict this, but we can't predict this in the real workload. We need to know that values from the both tables will be locked one by one. Yes? And this gives us pretty random expectation for the deadlock. And here, if we want to avoid the deadlock, we can, again, after we understand how this works, we can create several solutions. First one, we can remove the transaction. We will not have deadlock at all. We can use different isolation level here, like read uncommitted. Do not do shared locks and avoid deadlock. We can change the join. Yeah, we can use something like, let me put users here, statuses here, and let's do nested loop instead of merge join. In this case, we will not have the deadlock. Let me start the transaction. I'm starting my query. And second query, everything is fine. This query continues to execute. So, that's it. Again, we found the root cause and we found several solutions for it. Use or not use hints, this is your choice, but I think that at least as a temporary solution, this is a good stuff. Of course, if you will be fine with the performance of another type of join. Before going to the next topic, we need to refresh some knowledge about the logs. This time, update log. Honestly, SQL Server to update some data in the database or delete rows, SQL Server doesn't put exclusive log directly. And when SQL Server search for the rows to update, SQL Server mark that rows with update logs. And during this time, during this search time, other processes who want to update the rows will stay in the queue because SQL Server will see that they want to update the same rows, but processes which want to select data and put shared log will be able to do this. After first process will find all the rows to update, he will convert them to exclusive logs. And of course it will wait for the shared log to be released. When shared log released, it converts the last log to exclusive, and here SQL Server start doing the update. And after this, all processes are prohibited to request the data, both update, shared, and exclusive. Now we're coming to the demo, which I call when deadlock graph doesn't make sense. In this case, I will use again isolation level repeatable read, and in the first transaction I'm selecting user ID from table users, and then I update the users where user ID equal to my ID. That's pretty simple. And second transaction will be completely the same. So they both select same user ID and they both do update of table users. And that's interesting because they're doing the same operation, they're accessing data in the same order, but somehow they will deadlock each other. Let's check this. Deadlock happened. Let me stop the transaction. And let's check the deadlock graph. Here we go. Extended event session is asynchronous, so I need sometimes to stop to make sure that data came to the file. This is our deadlock. And what we see here, we know that both queries are the same, so let's try to analyze this output. First query, hold update lock on the clustered index of table users and request exclusive lock on the same index. We know that we're accessing the same data, and this actually makes sense because I showed you previously how SQL Server transfer update to exclusive lock. But the second query, hold update lock on the clustered index on table users and request update lock on the clustered index of the table users. And we definitely know that we are working with the same values. First of all, we select data by this ID from table users, and then we update data using this ID in table users. When you see something like this in the deadlock graph, when deadlock graph doesn't make sense to you, you need to go to the XML representation. It gives you much more information, much more valuable information about the deadlock. We have two sections here, process list and resource list, bubbles and squares. In the process list we can check everything related to processes. Wait resource, we can even find the actual row which was blocked here. We can find information about the transaction, about the connection. Very important that we can find here information about the isolation level, because it can be very important in the deadlock troubleshooting, and all other kind of stuff. Let's go to the resource section. And here we see that first process hold update lock on the table users, on the key in the table users in clustered index, and try to convert it to the exclusive lock. And at the same time, second process is waiting to convert something to update lock. Yes? And this is second resource, which is, in our case is the same. And here we see that first process hold shared lock and try to update shared to update. And now all this picture starts making sense, because we know that now shared locks hold till the end of the transaction. We put shared locks on the table users on this particular key, and then we're doing the update. So we need to convert shared lock to update lock first, and then to exclusive lock to make actual update. First query from these two transactions will convert shared to update, but will not be able to convert update to exclusive because of second transaction holding shared lock. And second transaction will not be able to convert shared to update because there is already update lock there. So now it makes sense. Now we can fix this deadlock. We can use different isolation level, read committed or maybe even read uncommitted. Maybe we can break this transaction. Maybe we can lock this resource exclusively at the beginning, like with xlock. This will prevent this transaction to hold shared lock on the same resource. Yes, because first one will hold exclusive lock, second transaction will stay here. And again, you see that we found the root cause, we found a bunch of solutions, and this is the main idea of this session. Next case I called object deadlock. In this case, we will continue using isolation level repeatable read, and in the first transaction I'm selecting all from statuses where user ID equals some value, and then I update statuses for this particular user. In second transaction, we'll select all statuses where user ID not equal this value, and then we will update statuses where user ID again not equal this value. So we are working with completely different data sets. Let's check if we will have deadlock here. Okay, it happened. We definitely have deadlock. Let's check our file. Here we go. And we see here in different square object lock. What it means? In this case and in a lot of other cases, object means table. So let's go directly to the resources. We will see these object log, sub-resource full, and object name statuses. So this means table log for the statuses table. And if we will check the deadlock graph again, we will see that query 1 hold shared log on the statuses table and request intent exclusive lock on the statuses table. While second process hold shared lock on this table and request intent exclusive lock on this table. So we have few new things here. First one, intent locks. Second one is why this is happening on the table level. We are selecting and updating rows again like we did before, but previously we did not have this object lock. Let's check few things. First of all, we will check lock escalation. If SQL Server is trying to update too much rows, it's something about 5000. So after locking some significant amount of rows, SQL Server decides that it's not efficient to hold all these locks, and it will be much more efficient to lock the table complete and hold just single lock. Each lock block take 128 bytes of memory, and well, it's 5000, it's not too much, but SQL Server thinks that it's too much. If it can't, SQL Server will continue blocking rows and will try to do table escalation each 1250 rows. This is the first case for escalation. Second case, if the memory for locks will become bigger than 25% of the overall buffer pool, SQL Server will do the lock escalation again. And it will try to do this lock escalation until the memory for locks will exceed 60%. After this, queries will start fail. Second concept, intent locks. When SQL Server wants to put shared lock on the key or on the row, SQL Server put intent shared lock on the table first, and then intent shared lock on the page. And then SQL Server put shared lock on the particular row. Using this schema, SQL Server gives enough information for concurrent processes where this shared lock is located. And if another process will want to block page or table with exclusive lock, he will see that there is shared lock inside, and he will not be able to put exclusive lock on that level. Now let's get back to our queries. So, both queries selecting big amount of rows much bigger than 5000. So, at this query, because we're using repeatable read, we will be locking more than 5000 rows, and SQL Server will put shared lock on the table level. And then when we want to do the update, SQL Server will convert shared lock into the intent exclusive lock. And in both cases, for both queries, SQL Server will not be able to do that because there is concurrent shared lock on the table. What we can do here, we can do several things. Again, we can choose different isolation level, we can drop the transaction, we can disable table escalation for this table, for the table statuses. we can block statuses here with exclusive lock, for example. Yes, or we can put even table lock. So we came to the same situation. We found the root cause of the deadlock, and now we can have a lot of solutions. Good, let's go to the next case, and our next case will be very interesting: range deadlocks. For this demo I have created a tiny database TwitterLite, which has the same tables, user and statuses we saw before, and different dataset. Let me show you this dataset. I have added famous SQL Server people to this table, and for this demo it's very important to know that Paul Randall and Kimberly Tripp are working for company SQL Skills. Kevin Klein and Aaron Bertrand are working for company SQL Sentry. This is very important in context of this demo particularly. Let's come to the queries. We will use transaction isolation level serializable, and let's check the details of serializable isolation level. Serializable isolation level is the most restrictive isolation level in SQL Server, and it helps to avoid phantom records concurrency effect. Let me show you what is this. Let's imagine we're still using repeatable read isolation level. We have transaction, we select stuff from users where city equal Houston. We hold this shared log till the end of the transaction, but another query is not updating or deleting these rows. It just inserts new values into this range. And this insert will happen without any issue. We will have a new record in the table with the city name Houston. And the second query in the first transaction now will return 4 rows. This is phantom record. And serializable isolation level helps to avoid this concurrency effect by using range log. So in this case, if we are selecting stuff from users where city equal Houston, SQL Server will put range log, and this will prevent insertion into this range by other queries. Insert will not happen, insert will wait while this range log is in place. And select query in the first transaction will return the same 3 rows. So in case of serializable, phantom records, repeatable, non-repeatable reads, dirty reads are not possible. And only after the commit, insert can happen and new value will be inserted into the table. Okay, let's get back to the demo. We're using serializable for both transactions. In the first transaction, we update user set company SQL skills without white space, where company equals SQL skills, and second query will return all statuses where user ID in company SQL skills. Second transaction, we delete statuses where user ID in select ID from users where company SQL Sentry, and then we delete all users where company equals SQL Sentry. So in these two cases, again we're working with separate data sets. First transaction works with the users who work in company SQL skills. Second query works with users and the statuses of users who work in company SQL Sentry. Okay, so on logical level, these two transactions should not intersect. But in SQL Server, they will intersect and we will have a deadlock. Okay, looks like deadlock happened. Let's check this. Deadlock, wow. Let's go to the deadlock graph. Here we go. This is our deadlock. You see these range logs. Range SS means range shard. One log is for the interval, one letter is for the actual values. And in this particular case, looking into the XML representation of deadlock graph, looking into the query plans will not give us enough information to understand the root cause. For understanding the root cause, we need to go deeper and we need to check which rows are actually locked in these transactions. Let's do this. I will open the transaction and do the first update. User set company SQL skills where company SQL skills with white space. What we see here, 2 rows affected, that's expected because we're updating rows for Kimberly Tripp and Paul Randall who are working in SQL skills. But if we will check the logs for this session, actually I will check just range logs. If we will check logs for this session, we will see that 3 rows locked. And that's pretty interesting. 2 rows locked with range XX, and probably these are 2 rows which we are updating. And we have an additional lock range SU. Wow, let's check what is this. To check this, I will use hidden function lockRes. I will call it for each row in the users table and you will see the results. Each row in the index contains this hidden field. This is a hash of the key which SQL Server used to store and check logs in the internal log hash table. And running this function on the table, I will get the values of this hidden key and can compare to the resources blocked here. So if we will check this 3rd row blocked, we can clearly see that this is Kevin Klein from SQL Sentry, which means that even if we are updating the users who are working in SQL skills, SQL Server blocked just another row to prevent the insertion into the interval. And this is the magic of serializable. There is no exact magic there, it just blocks a bit more rows. And in some cases, it can lead to tricky deadlocks, like in this case. Okay, we found the root cause. What we can do with this? How can we fix this deadlock? Of course, we can consider not using serializable, change logic of our application, change our queries to avoid such kind of intersection. Okay, let's go to the next demo, next topic, next deadlock, implicit deadlock. In this demo, we will be using read commit snapshot isolation level. I set it for my database Twitter for this demo, and this will mean that for each query which will be running with read committed isolation level, SQL Server will use read committed snapshot. Let me show you this. Right now I'm in database Twitter, and if I will check isolation level, it will show that my isolation level is read committed snapshot. Okay, let's check what is this and how it affects the logs. So with read committed snapshot, SQL Server will not use shared logs for reading data. If I select stuff from users where city equal Kyiv, I will select this row without putting shared log here. Even if other session will update this row, I will be able to read, but not this particular row, I will be able to read the previous version of this row. Yes? When transaction update value in the table, it has to store the previous value into the version store area in tempdb. This is pretty fast insert because version store is the only place in SQL Server, if I'm not talking about in memory tables, where SQL Server will not use transaction log. So this insert will be faster than the regular insert. And when second query, select query will come, and we'll see that this row logged with exclusive log, it will not wait, it will go to the tempDB instead and get the previous version of this value. Good, let's go to the demo. First transaction, update users, set name equals Santa Claus and back to Santa, and then do insert into table statuses. Second transaction, which is just a single query, just insert new values into the table statuses. Let's check if there will be deadlock here. Deadlock happened. Let's check this. Here we go. And let's check the deadlock graph. Here we go. So, I will go directly to the interesting point. We see a bunch of exclusive log, but what is this? The query which was killed by SQL Server requests shared log to the table users. This is this single insert trying to access table user. And the key to this puzzle is inside the query plan of this query. This is clustered index insert operator, and you see the lookup to the users table. Why this is happening? Because statuses table has a foreign key to users table. And SQL Server, this works in every transaction isolation level, and this is not under the rules of transaction isolation level. SQL Server need to keep consistency for the operation. You need to prevent deleting the user value in the users table or changing this value while we are inserting data into the statuses table with this user key. To do this, SQL Server choose the most lightweight log, which he can use here, and this is shared log. So this is why we put exclusive log on the clustered index, and then we are requesting data from users table and put shared log there. In between this operation, this transaction trying to update users and then to insert data into the statuses table. Okay, we've got the root cause. What we can do with this? Maybe we can consider changing this transaction, not updating users before inserting to statuses. We can drop foreign key. This is definitely not a good solution, but it will work for sure. We can create transaction here and log the related records in the users table with exclusive log or with update log, and this will work. So that's it. We have a bunch of solutions. Now we need to choose something from them. In this particular case, all the solutions are not too good. Yeah, but we have that solutions. Okay, let's go to the next part of our session, and this will be NOLOCK deadlock. Before going into this demo, let's remind the NOLOCK and read uncommitted isolation level concept. Read uncommitted is the most lightweight isolation level in SQL Server, and using read uncommitted on the session level and using NOLOCK on the table level will mean the same. Yes? But if you use read uncommitted on the session level, it will apply to all the tables in this query, which will be running in this session. Okay, how it works? We're selecting data from users where CT equal key. If SQL Server will not put shared log for this read, we run transaction which update users and change city to key where city equal New York. This transaction hold exclusive logs on these rows. We run second select query with read uncommitted isolation level. And this query will return us 3 rows. Then our transaction can be rolled back and we will have same records New York in the table. So our next select query with read uncommitted isolation level will return just single row. What happened in the second query we call dirty read. This query reads the data which never exists in the users table. This is not the only one side effect of NOLOCK. NOLOCK is a bit worse than just dirty reads, but this is a bit another topic. So right now we need to remember that there is no shared logs if you're reading data with no log hint or with read uncommitted isolation level. In this demo, I will run several queries. First one, we'll select data from table new statuses and new users, both with no log hints. That means that there will be no shared log for this read. And second query will execute some procedure which called quick update. I will show you later what's inside. Let me run these queries, and after a while, first query failed with the deadlock. Let's go to the deadlocks, graphs, and see what is happening here. This is our select query, and you see that even with no log hint, this query put some kind of log, schema stability log, which prevent other processes from table schema modifications, like other process can't drop the column while this query is executing, because this will be not good. And this schema stability log can be blocked only by one type of log in SQL Server, schema modify log. So our procedure quick update puts schema modify log to both table statuses and users in different order. That is why we are getting deadlock here. Let's look inside this procedure, quick update. What's there? So, this is it. We're disabling triggers on both tables, new statuses and new users, and then we are enabling the triggers. This puts schema modify log for a short period of time, but it's enough for us to have the deadlock. Because if deadlock can happen, even if the time interval is very small, deadlock will happen. We find the root cause, how we can fix this. Probably it's not a good idea to disable and enable triggers to increase speed of update. We need to find some another solution. Maybe we can completely go out from triggers. We can rewrite this logic into the update procedure or something like that. But definitely we should not use enable disable trigger to speed up some operation. Okay. Let's go to the next demo. Next case, called hidden deadlock. In this demo, first query will update table new statuses, and second query will update table new users. Even in comparison with previous demos, this is pretty unique. We are updating completely different tables. How deadlock is possible here? Okay, we have deadlock. Let's check our deadlock graph. That's very interesting how it can happen. And when we will check the deadlock graph, you can see that both queries accessing both tables, users and statuses, even despite that fact that they are updating just one of them. So let's go to the XML representation of the deadlock and we will see this, the root cause. So, what is this? Proc name tr new statuses update. This is some kind of hidden logic inside, and this hidden logic is trigger. If we'll check our tables new statuses and new users, we will see some trigger which updates another table as well. So we're updating statuses, and in the trigger we're updating users. And we have trigger on the users table which updates statuses. That is why we have this deadlock. How we can prevent such kind of deadlock? Of course, this logic is false. We don't need to use something like this, updating tables in the trigger, vice versa. This probably will be the right choice to avoid this deadlock, but definitely we have several options here like we had in previous cases. Okay. Next case is not so infrequent, but it's very interesting because in this case single query can be deadlocked with itself. It's very hard to do this demo on local environment, and I'm really grateful to Paul White for sharing this demo script. So I will run it on different instance. I will run it on SQL 2017, and it will take about 10-15 seconds to execute. Also, this kind of deadlocks called intra-query parallelism deadlocks. When query have several threads and SQL Server sync these threads in the middle of the execution plan, let me show you the execution plan here. There can be a situation when this can't happen smoothly, yes? And deadlock can happen, yes? We will not see the beautiful graph here, but we can definitely see this information. Yeah, and in resources section, we will see process will be the same. In resources section, we will see something like this: exchange event, wait type, pipe new row, and so on and so on. So what happened with SQL Server when this deadlock occurred? SQL Server just tried to restart the blocked and killed thread, and usually this will not cause query fail. SQL Server will just restart these internal threads and the query will finish, but it will take a bit longer time to execute. But in some cases this can even fail the query completely. So this can be considered as a SQL Server bug, because SQL Server can do its job for threads synchronization. And what we can do in this case, we can remove parallelism completely with max degree of parallelism 1. Yeah, maybe it will help query to execute faster. We can rewrite the query or add some hints to fix the query plan and avoid this situation when query starts blocking its own threads. And these cases, intra-query parallelism deadlock, are fixed in the cumulative updates for SQL Server from time to time. So maybe going to new SQL Server version will also fix this issue. Okay, what do you think now? Is this the most weird case of deadlock? Well, it might be, but our next case just said, hold my beer. This will be much more unusual, undetectable deadlock. This is a very unusual situation, and in my experience it happened just twice. So for this demo I would like to say thank you to Erland Sommerskog and Adam Mechanic, who together created this repro. So I will use AdventureWorks 2012. Actually, this is Big Adventure, database created by Adam Mechanic. I will run the transaction and delete one row from big transaction history. Let's go. In the second session, I will run some complex query. Then I will go to the first transaction and run my update. Okay, at this point, these two sessions block each other. But SQL Server can't detect this situation as a deadlock. If we will check the requests, our sessions are 77 and 76, we will see that session 76, this is our transaction, blocked by session 77, but session 77 is not blocked by any other session. If we will go deeper to the DMOS waiting tasks, to the threads of these requests, we will see that session 77, at least one thread, blocked by session 76, and session 76 blocked by session 77. So this is clearly a deadlock, but SQL Server can't detect it. And on the request level, you saw that there is no deadlock. On the request level, SQL Server thinks that everything is fine and session 77 will finish. In this case, it's very unusual, it's very infrequent, but what we can do in this case? We need to become deadlock monitor and kill one of these sessions. Let me kill 77, and immediately session 76 was finished. This situation also can be considered as a SQL Server bug, and from time to time development team release patches for it. If you will check cumulative update, you will find some fixes for such kind of situation. And at the same time, this is very infrequent, but the consequences of such kind of deadlock can be much bigger than for any deadlocks we saw previously, because this can completely stop the system. In this case, I would recommend to create support ticket to Microsoft and try to rewrite these queries or business logic for these queries to avoid this kind of intersection which cause this undetectable deadlock. Okay, that was the last deadlock I wanted to share today. And as a summary, I would like to share some thoughts about deadlocks and 3 rules of deadlocks which I found during all these years. First rule: if deadlock is possible, it will happen, even if the time interval for the queries and locks intersection is very, very small. Second rule: deadlock should not be solved before the root cause was found. And this is the main idea of this session. You saw many times during the session, during the demos, that first of all we are going deep and find the root cause of the deadlock. After that, usually we have several solutions from which we can choose from. And the last one: there are no unsolvable deadlocks, but there can be solutions which will not satisfy you completely, like dropping foreign keys or using NOLOCK. But there definitely are some solutions. Okay. How we can avoid deadlock? Design database to avoid possibility of deadlock, but that's definitely impossible, almost impossible. But we can do some things, some good things, which will reduce chances of the deadlocks. We can modify tables in the same order in our application, in our database. We can choose appropriate transaction isolation level and not go in with the serializable if it's not required. Consider optimistic isolation level like snapshot and read committed snapshot. These two greatly reduce the chances of the deadlock and general blocking in the database. Keep transaction as small as possible to reduce the time needed for deadlock. And the last one: if possible, use stress testing for your application or database. Put much bigger load that can be in the system, just to catch this situation when 2 threads, when 2 processes can block each other. I hope that information from this session will be helpful for you and will help you to avoid as much deadlocks as possible. Thank you for attending.